All right, so enough of that. Inclined plane. I know this is what you guys have always dreamed of. The inclined plane problem. I mean, it really is the beginning and the end of all physics. Here it is, guys. The inclined plane. This is it. So now, so what that means for the inclined plane is we automatically consider the case with friction. Inclined plane with friction. So what does that look like? Well, it looks like an inclined plane, of course. No, that is not an inclined plane, Mr. Cleo. I have yet again failed at doing another thing. So, call that theta. Call this the right angle. Okay? And what else? Oh, we need to put something on there. We put a block. Okay? Now what? Free body diagram, Ariana. Spot on. So, what are the forces acting on this? Gravity. And where's gravity acting? Straight down towards the center of the Earth. This is Fg. What else? Normal force. Where's normal force acting? Perpendicular to the plane. That's right. You know what? I'm going to be a little bit more exact. Oh! There we go. What else? Friction. Where's friction acting? You sure?
Yes. I'm positive.
But what if I push it up? That's a good question. Why would I do that? What we'll do is we're going to incorporate that case in a little bit. In fact, you can see exactly where I will incorporate it if you look ahead on the board. But for right now, I'm going to say Andrew's right, like usual, and have it go up the plane. So, now what? What do we need? We need a? No, you're too quick. We need a coordinate system. And that coordinate system is going to actually simplify this problem pretty tremendously, depending upon which coordinate system we choose. So which coordinate system do you want to choose? One which is the easiest. Of course, we're lazy. So which one is that? Be careful. Anyone else? Wait, which way? Anyone else? Slanted. It's definitely the easiest coordinate system. Why? It's not so obvious that you would do a coordinate system which is directed like this. Very good, Andrew. What Andrew just said is actually kind of brilliant. He said you're going to choose the coordinate system where the majority of forces align with the axes. So if you take a look, how many coordinate systems align with the axes if we take our normal xy coordinates? If we take that coordinate system, which one aligns with an axis? Only FG. But if we change our coordinates to be, you're not nice. This guy just won't erase. Of course. Okay? If we change our coordinate system to one which is perpendicular to the plane, or excuse me, which is parallel and perpendicular to the plane, then which vector do we have to break up? FG. Only one vector. But Zezel, he's got something in his head. He doesn't like this. And he doesn't like this because he has a friend who's a carpenter. And he calls up his friend. And he needs to call up his friend who's a carpenter. And why does he need to call up his friend? What do you need to do in order to use that coordinate system? You need to do something very important. You need to nail this plane into the floor. Why? So it doesn't what? Yeah, it's okay if it moves. It can't accelerate. Why can't it accelerate when we're using this coordinate system? Because this coordinate system is attached to the plane. So if the plane accelerates, what happens to the coordinate system? It accelerates, therefore, Newton's laws are violated. Very good. Now here's a question. Let's suppose that you don't have your iPhone. Oh my God. Question's invalid. Invalid question. Let's move on. So, let's suppose you can't call your friend who's a carpenter. Don't ask how he actually got those nails in there. All right? But you can't call him. So in other words, you can't nail this to... That was not fair. Ah! Ah! Whatever. Let's suppose you can't nail these, okay? Do all your teachers have this many technical problems? Why is that? Okay. Oh. Okay. So now, let's suppose you can't nail this, right, to the floor. What would you do? What do you need to do in order to actually solve this problem, which is not an easy problem? This is a hard problem. You need to construct inertial coordinates. Well, where are you going to put inertial coordinates? Outside of the plane. You would have to put it out here. And then you'd have to describe not only the position of the box with respect to your inertial coordinates, but the position of the plane. And then you'd have to understand how they accelerate relative to one another. Very difficult problem. If you're interested, I'll be here after school and I can actually work through this problem for you. It's a great problem, though. Not easy. But anyhow, let's go back into reality. And in reality, we have friends that can nail planes to the floor. Now what? Now we need to break down our vectors. Which vector are we going to break down? FG. So we'll break it down to a component that is parallel to the y-axis and a component which is parallel to the plane. Parallel to the plane. Does that look right? Ah. So this is a 90-degree angle. This is FG y. This is FG x. So in order to understand what FGX and FGY is in terms of FG, what do we need? We need an angle in there. So how are we going to get that angle? Geometry, naturally. So what is this angle? Someone tell me. You sure? All right. So let's be sure about it. How are you going to make sure that's theta? I need a geometric argument. How can you tell that this angle is theta? It is. We know it is. But it's not. That's only because of the triangle that I drew. If I drew a triangle that was closer to a 45, 45, 90, you'd have no idea. Yes? Which two lines? This and this. Very good. So therefore, this angle is? That's 90 minus theta, right? What else? Continue. No, I want to hear your logic.
And then I was just thinking about, like,
Correct. This is parallel to that, correct?
Yeah, so then FG would be like the thing that intersects.
So in other words, this is perpendicular to this.
Yeah.
So this is perpendicular to that, which means that is a 90-degree angle.
Then that's theta.
That must be theta. That's right, because if we call this alpha, then alpha, if we call this alpha, then we have alpha plus 90 minus theta equals 90, which tells you that alpha equals theta. And notice how I use that trick over and over again. I call something alpha, and I show that alpha actually equals what I want it to equal. It's the trick of the trade. So that's theta, and so now I can actually draw that triangle a little bit more specifically. Does that look right? Ah. So this is FG, that's theta, that's FGY, that's FGX. And so what's our relationship then? We have that the sine of theta is equal to what, guys? FGX over FG. Welcome back. And the cosine of theta is FGY over FG. All right? So now we can begin writing Newton's second law in each direction, because that's the only one that we had to worry about. So FGY, we get FGY equals FG cosine theta equals mg cosine theta. And we get FGX equals FG sine theta equals mg sine theta. What else? So now we write Newton's second law. We have net F in the x direction equals max. And so what's the net force in the x direction?
mg sine theta minus.
Let's write it in terms of the actual components first, and then we'll talk about the values. FGX minus FF equals max. And similarly, we have Fn minus FGY equals may. But what can you say about ay? Why?
Because this thing's not floating up in the air.
How is it actually not moving? Tell me. What is the precise movement it's not doing?
Not moving perpendicular to the surface.
Correct. When you go and you let this go, like this, what you don't observe is this thing start accelerating this way. In other words, the acceleration in this direction is 0. The acceleration is confined purely on the plane. So AY is 0. As a result, we have Fn equals FGY equals mg cosine theta, based upon what FGY was. So now we go back to the x direction. Here's the x direction. Because really, by solving for Fn, what did that really do? What's the real purpose for solving for Fn? That's right. Fn uniquely determines FF. So FF equals mu Fn equals mu mg cosine theta. Now remember, that's not always going to be true. That's going to be true in two cases. Which two cases? Which two cases is that going to be true? And then think about which are the two cases of friction where you can write FF equals mu Fn? Which static? It's not all static. Be careful, guys. Maximum static friction and kinetic friction. Those are the two cases where you can do this. So you might want to write that down. Just as a reminder, because it's been a while since we've been in forces. Wait, did we take the exam before the NGA-EA break? Oh yeah, forget about it. Definitely write that down. All right, come on now. So now, I'm going to go back to the net force in the x direction. And I'm going to rewrite this. We have FGX minus FF equals MAX. Now, if I wanted to take into account both cases, what would I do? I would write minus plus. What does that mean? Yes?
Depends on whether you're pushing it up the hill or it's going down the hill, just the side.
Correct. If I'm pushing this up the hill, let me actually use something that has friction. So this guy. Oh, man. So, I push this up the hill. Which way is friction directed? Down the hill. I push this down, I push this down the hill. Which way is friction directed? Up the hill. So the first case, we had this thing moving down the hill, right? But down the hill is what direction? Positive or negative? Positive. So friction is in the negative direction. So if we're going up the hill, which way is friction? Down the hill, which is positive, which is why you have FGX minus plus FF equals MAX. So we can write this. What is FGX? mg sine theta minus plus, what's FF? Mu mg cosine theta equals MAX. We can solve for AX. We get AX equals So now the first thing we have to do is test the reasonability of this. So the first thing we do to test the reasonability of this is we turn off friction. So here's our expression. Our expression is AX equals G sine theta minus plus mu G cosine theta. Turn off friction, meaning mu equals 0, implies AX equals G sine theta. What happens if theta is 0? Sine of theta is 0, which means the acceleration is 0. Does that make sense? Yeah, in other words, this is on a flat surface. Is that thing going to accelerate? No. When is that going to be maximized? When theta equals 90 degrees, right? Theta equals 90 degrees corresponds to what? Straight drop. In other words, I take this thing, right? I have a pivot, and what do? I drop it. And it drops like a rock. So, does that work? It works. Does that make sense? Notice, if there's no friction, what's the maximum acceleration it can have? G. So now let's turn on friction. We turn on friction, so now mu is not 0. And what can you tell me? Is it possible for the acceleration of the object to be greater than g if you turn on friction? Talk about it for a minute. See if you can come up with a scenario in which the acceleration exceeds g. Anyone? Anyone have a scenario where the acceleration would exceed g? I'm not even sure if that's true, if it's possible. It has to be quite a unique circumstance. But consider this. Let's suppose I take this plane. Does anybody have any scenario? Suppose I take this plane, put it on a pretty high angle. I think I need someone to help me. Thank you, sir. So I put it on a pretty high angle. Right? At what point would the acceleration possibly have exceeded g? Anyone? Take a look. Come on over here. Or if you don't believe this, let me get something that's a little bit more extreme. Need this? Yes, this might be a little bit more extreme. At what point would the acceleration... Is the acceleration uniform, yes or no? Why not? Which path is the acceleration greatest? See if you guys can identify it. During which, but yes?
You mean the magnitude or?
Magnitude. Think about the direction of the vectors. Anyone? Come on now. You got a 50-50 chance. Is it up or is it down? When it goes up. Why when it goes up? More. No, there's no applied. What are the forces acting on it? Gravity and friction are both acting down the plane. So it's possible to arrange a set of materials, right? We have specific materials at a specific angle, right, such that when you go and you propel this up the plane, that the acceleration down exceeds g. Why? Because the friction and g is going opposite the direction of motion. In other words, it's going down the plane. And so this is why it's a little bit tougher. Thank you, sir. It's a little bit tougher when you're dealing with 2D motion, because friction can really go both ways. Any questions on that? You sure? Come on now, guys. You know what this means. This means we go to inclined Atwood. So here it is, guys. Come take a look at this device. And this is the inclined Atwood with friction. You wanted cyanide, you got it. And here it is. And this is a beaut. So if you take a look, all right, and I can demonstrate both cases, why I was kind of very careful in talking about up and down the plane. Because it's pretty easy for me to actually send this thing up the plane. What would I do? Just add mass. That's right. 1, 2, 3, 4, 5. Right? And how can I send it down the plane? Take mass off. Right? Just 1, 2, 3, 4, 5, 6, 7, 8. And this is actually a very interesting interaction of surfaces. Because when you play with this for a little bit, you realize that actually this has a non-uniform coefficient of friction. You can feel it on there. But anyhow, let's start. So, because I want to make sure, although you guys are going to be as prepared as, you're probably going to be the most prepared class of all of them, which is not surprising because guess what? There's a reason for it. What's the reason? You missed class the least. Or in other words, you have, as far as I could tell, you guys missed the least amount of time all year. But, whatever. This is how, such is life. So now, we go and we draw this scenario. So yet again, we're going to go with the easiest case. Easiest case is that inclined plane is? No. We're going to deal with friction. We're tough guys here, all right? But the inclined plane is going to be nailed to the floor. And you can kind of imagine what would happen if it wasn't. If it wasn't nailed to the floor, think about what the consequences would be. So, this is pretty hideous. You know, you guys aren't really critical enough. You need to really, I would really appreciate a harsher critique of my artistic skills. Ah! And the reason why I'm fiddling so much with the board and didn't just give up on it is because I'm recording it. Oh, God. I'm losing it, guys. This is so brutal. This is like an exercise in... That's going to have to do. I'll just fill in that space. All right. Pick a direction. And this is how you generally want to do this. Pick a direction. In other words, which way do you want this thing to go? Down the plane or up the plane? So you want it to go up the plane. So in other words, this thing is going like this. Now, I'm going to solve this formally, but I want you guys to do the systems approach for homework. To solve this, to solve for the acceleration of the system using the systems approach. Which do you think is going to be easier? Systems approach by a long shot. You wouldn't dare do this on an exam. Unless, of course, I instructed you to. You know how it is. When you're a teacher, you do crazy things. So this is M1. This is M2. What are the forces on M1? So we need a separate coordinate system for M2. So for M2, which way do you want to go? Which way do you want this to go? You tell me. What do you want up to be? You want up to be negative? I'd be careful. Look at how the system accelerates. Right? This is going up the plane. So therefore, if up the plane is negative, then you want down to be negative as well. Does everybody understand why? Why? In general, even period, like why would you want to say this is negative, this is positive? So therefore, A1 equals A2, as opposed to A1 being negative A2. This is also what we're familiar with. So looking at this right off the bat, we know A2 equals A1. And the reason is because this is accelerating down, right? M1 is accelerating up. And we have up the plane as negative. So now what? Now we do a free body diagram on each. Massless pulley, massless string, what does that tell you? Tension's the same. So on M2, where are the forces on M2? Tension and gravity. Do I need a free body diagram? Here. Here's my free body diagram. You have Ft minus Fg2 equals M2A2. What about on M1? Forces on M1? So let's be a little bit. Fg, where's Fg pointing? Straight down. What else? Normal force is? That way. What else? Friction is? Down the plane. What else? Tension is? Up the plane. And so now you really see the benefit of this coordinate system, right? Because now how many vectors are aligned with the coordinate system? And only one needs to be broken down. Which one do you break down? Fg. And you can see Fgx is going to be, come on now. Do we need to do this again? That's, so it's going to be Fg cos theta, which is, sine theta, which equals mg sine theta. And likewise, Fgy equals Fg cos theta. And so now for M1, what do we have? We have Ff is going down. We have Fgx is going down. And that's actually Fg1x. And we have Ft is going up, so it's minus Ft. Are there any other? Nope, so that's equal to M1A1. And so now, before I even start writing anything, in other words, start filling in, what should I do with these two equations? Well, A1 equals A2 equals A. So this becomes M2A, and this becomes M1A. Now what? What can you do with these two equations? How about you add them? When you add them, what do you get? Or better yet, what cancels? What do you get? The FTs cancel, right? So you're left with Fg1x, right, minus Fg2x, Fg2, there's no x component for Fg2, plus Ff equals M1 plus M2 times A. But then you notice something. You say, wait a second, Khalil. If this thing is accelerating this way, Ff is pointing down the plane is positive. And what happens if it's accelerating this way? It's going to be up the plane negative. So how can I resolve both of those scenarios? Plus or minus. There you go. I shrink this further. And now what? This thing's so crazy. Now I use the y direction for mass 1. What's the net force on mass 1 in the y direction? So M1 y direction. We have Fn minus Fg1y equals M1 A1y. But the question is what is that thing? What is that? What is that acceleration? The acceleration of M1 in the y direction. It's 0. Why? Because what do you never see this thing do? You never see it go out off the plane like this. If you do, you run. That's right. It's time to run. That's right. So A1y is 0, which tells you that Fn yeah, real cool. Equals 0, which means Fn equals Fg1y, which equals M1g cosine theta. And what does that allow us to do? That's right. It allows us to write FF. FF equals mu Fn equals mu M1g cosine theta. Oh, now I feel like I'm running out of time. Likewise, what is... Oh, man. Now we can actually begin subbing in. Fg1x is equal to what? M1g sine theta. Fg2 is M2g plus minus, what's FF? Mu M1g cosine theta. And that's equal to M1 plus M2 times A. Whew. So solve for A. I'm going to use A is equal to M1 g sine theta. Right? You can. Minus, you can factor out, oh wait, you can factor out a g. But first, let's actually just investigate this. M2g plus minus mu M1 g cos theta, all divided by M1 plus M2. So now we need to actually assess the reasonability of this. So to assess the reasonability of this, we have to look at limiting cases. And what are the two limiting cases of this apparatus? The one limiting case is where theta equals 0. When theta equals 0, what should this reduce to? What apparatus should it reduce to? Table Atwood, right? So let's investigate theta equals 0. So when theta equals 0, what does A equal? Now, which scenario gets applied? Minus or plus? It would be? That's right. So it would only be plus. So it's going to be mu M1g cosine theta, right? Over M1 plus M2. So cosine theta goes to 1. And what do you end up with? Notice that acceleration means what? Let's disregard the sign, because the sign means what? It's going that way, which we normally called positive direction. So what does this reduce to? It reduces to, if you look at the magnitude of A, it's going to be M2g minus mu M1g over M1 plus M2. Or if we switch the directions, let's not even look at it from the standpoint of magnitude, but if we switch the directions, Do we retrieve the table Atwood? Yes or no? Is that the acceleration of the table Atwood? Well, think about it. Mu mg is mu Fn for something that's on a table, right? Because Fn equals mg. So we get the weight, Fg, minus the force of friction. Is there any other forces on the system? No. So it reproduces the table Atwood. Now, let's look at the hanging Atwood. What would the hanging Atwood be? Theta equals 90. So theta equals 90, what do you get? You get the acceleration's equal to pretty incredible, right? So now, what do we have to solve for? We have to solve for the tension. Oh, man. So we have A. Now we have to solve for Ft. Right? We have A. What's A? That's A. So what body would you use to solve for the force of tension? Why? That's right. So for the hanging body, you have Ft minus m2g equals m2 times A. But what's A? Could someone read it off to me? Sine theta, right? Minus m2g, and then it's plus or minus okay, all over m1 plus m2. Okay? So I'm going to carry over that m2g. Get Ft is equal to m2g plus, I'm going to start multiplying, because God knows I'm running out of time. What's that, m2g? Right? m2 squared g. And then you got plus minus mu m1 m2g cosine theta. And this is all over m1 plus m2. And now I need to form a common denominator. The common denominator I'm going to form is m1 plus m2. So you have Ft is equal to m2g times m1 plus m2 plus, oh God, m2 m1g sine theta minus m2 squared g plus minus mu m1 m2 g cosine theta. All of this is over m1 plus m2. So you have Ft is equal to m1 m2 g plus m2 squared g plus m1 m2 g sine theta minus m2 squared g plus minus mu m1 m2 g cos theta, all divided by m2. Do we have cancellation? You bet we do. What cancels? Boom. That's what we get. That's the cancellation we get. So now, we have Ft is equal to what does it equal? I can factor out m1, m2, g. We have a 1 plus sine theta plus minus mu cosine theta over m1 plus m2. Limiting cases. First case we want to investigate is table Atwood. Table Atwood is theta equals 0. What is Ft? But remember, that becomes just plus because friction can't drive the system. And then theta equals 90. What do you get? This is and so the inclined Atwood is precisely like it is the entire system. It's the whole kit and caboodle. If you understand the inclined Atwood, you understand basically all Atwoods, because in it contains everything else. Any questions? I know that was a pretty intense algebra session. Yes?
I know this is pretty minor, but I still don't get why it's plus or minus.
Oh, okay. So it's not minor at all. It's actually fairly sophisticated. Because what you're doing is you're compensating for both cases simultaneously. And the idea is that it's not so much that it's going to be plus or minus. It's one scenario is going to be plus. One entire physical setup is going to be plus, and the whole other physical setup is going to be the minus. So in other words, this is going to be the plus. Wait, which way is friction directed when this goes down? Down, so that means friction is down, so that's positive. This is the scenario of the plus. Notice it's an entirely different problem. It's not like solving a quadratic, where both answers are solutions to the equation. This is one physical setup. Force friction's down the plane, which is positive. And then this is the other physical setup, where the force of friction is force of friction in this case is up the plane. Therefore, it's negative. So, and you should write that down. Make sure you write that in your notes. Anyone else? Like, do you have any questions, Casey, for coming in, like when you came in?
I had a question on homework, but I think you answered it early in the lecture, so I'm gonna watch that.
Which question was it?
It's basically like before when you were saying that for like the force of gravity on M1,
Mm-hmm.
it's equal to mg sine of theta.
Yes.
That's has to be the angle, right?
Correct. When you actually go and you decompose, if you go back here. Later, guys. Have a great day off tomorrow. Whatever tomorrow may be. Do your homework, by the way. Make sure you guys do all the problems you can. Sure.